ladies and gentlemen, we're going to start our final chapter, you lucky dogs. We're going to start chapter 10. It is our Conics sections. Today we're going to be mostly doing a pre-calc review and basically just kind of going back through information that you learned in pre-calc. Sorry. We're going to first talk about the characteristics of the conics. We're going to talk about circles, parabolas, ellipses, and hyperbolas. And then we're going to talk about the standard equations for each of those conics. And then we're going to get a general conic equation and do completing the square to fix it. So you guys know that my artwork is not spectacular. But let's say I have this situation, and I'm telling you, it's just not going to be pretty. I have this situation, which is called a napped cone. And then I would consider, just laughing because it's going to be bad, I'm sorry, running a plane through, and maybe the intersection between the napped cone and the plane might give me an ellipse. So, I'm sorry it's gruesome. So we'll try to make this be a little bit better as we work through some of our shapes. So the first one that we want to talk about is a circle. Well, the circle, we all know what they look like. We know that it has a radius that is the same from the center point to a fixed point, which is the outside edge of the circle. So a definition of a circle is that it is the locus of all points that are equidistant from a fixed point. Okay, so that just makes perfect sense, but it is the locus of all points, which sounds really weird. So it's just a collection of points, all of whom are equidistant from a fixed point. Well, the standard equation for a circle is x squared plus y squared is equal to r squared, but we're never satisfied, so we have to shift things and move things. So I get x minus h, y minus k is equal to r squared. In this one, my center of my circle is the origin, and the radius is the square root of r squared, which is just r. And then in this one, my radius is still r, but the center of the circle is now going to be h and k. So the circles are actually pretty boring, nothing too exciting as we consider the equations for a circle. The next shapes that we want to consider are a parabola, and we've done parabolas for a million years, but when we start talking about parabolas in terms of conic sections, then we add some cool additional language. So let's say here's my coordinate system. Here is my parabola. Okay, this is going to be the vertex of the parabola. Inside the parabola is a focus. I'll write the word up here. So the focus is what generates the curvature or helps to generate the curvature of the parabola. If I push it in and make it closer to the vertex, my parabola spreads out. If I pull the focus up, then it makes my parabola taller and skinnier. The distance from the focus to the vertex is called P. And then the distance from the vertex to the directrix, I'm going to do that in a different color. So I have an equation out here, and this would be my directrix. So the distance between the vertex and the directrix is also P. So the distance between the focus and the directrix is 2P, and the vertex would be at the center. So you can see that our equations get to be a little bit more entertaining. So the way that we write our standard equations would be 4p, and then my y equals x squared. If y is positive, if my 4p is positive, then that means that my parabola goes up. And if my 4p is less than 0, that means that my parabola goes down. Alrighty. And again, just like with a circle, we're not happy with it in its form like this. We need to translate everything. The unusual thing with the equations in this particular format is that in all of the other math that we have done in previous years, we would typically isolate the y and then push everything to the other side. But in this particular equation, we want to make sure that k stays with y, and then keep it inside the parentheses, and this value that's outside is going to be 4p, and that's what helps me determine the location of my focus, okay? Alrighty, so then the other equation would be, 4p times x minus h quantity squared is y minus k quantity squared. So again, in this particular parabola, it's either going up or down. Okay, those are your choices. Depending on the sign of 4p, this is basically x is equal to y squared, so we could write that over here. 4px is y squared. If the 4p is positive, then it opens to the right. If the 4p is negative, then it's going to open to the left. And so that's basically like your square root function. Okay? And then same thing here. If the 4p is positive, then it opens to the right. And if the 4p is negative, so we'll put little pluses there. And then here's a negative and here's the negative. Then my curves go to the left. There's a couple of different vocabulary that we need to consider when we talk about a parabola. The first one would be a focal chord, not your vocal cord, but a focal chord. And this goes through the focus, goes through the focus with endpoints on the parabola. You guys should feel blessed because I just hung up on my daughter. Shame, shame. So the focal chord goes through the focus and it has endpoints on the parabola. So I could have a focal chord, I could have a focal chord. Alrighty, and then another word, my latus rectum, awful phrase, is the focal chord that is perpendicular to the axis. And remember, when we use the word axis, we're always talking about the axis of symmetry. Alrighty, the only other thing that I did not put on this drawing was the axis of symmetry, but you've been there, done that for a million years, and you know that the axis of symmetry goes through the vertex. All right, so our next conic that we're going to talk about, let me move my paper back down, is the ellipse. And I think ellipses are pretty cool because basically it's a circle that's been stretched unevenly in one direction. So let's say I have this cute little ellipse, okay? So if this had started life as a circle, so let's say it started life as a circle, and then I stretched it in the horizontal direction, and I didn't stretch it in the vertical direction, then this would become a horizontal ellipse, okay? We're going to call the distance from the center, so I'm going to try to get some colors in here so you can see all the language. The distance from the center to the end of the major axis, so I have two different types of axes. I have a major axis and a minor axis. Major obviously means it is the longest, and then minor would be the shortest, okay? The major axis from the center to one edge is A, and then from the center to the other one is A. So the length of my major axis is 2A. All right, if I bring in another color, the way this particular ellipse is drawn, my minor axis is going to be the vertical axis, and it would have a length of 2B. Okay? Well, just like with the parabola, I know it's getting kind of busy in here, I have foci. The foci are always going to be on the major axis, okay? And the distance from the center of the ellipse to the focus, one is a focus, two are a foci, is going to be C. So this little distance right here is C, and this little distance right here is C. And the foci would be equally placed, alrighty? So, because of, I could draw you lots of pictures. The book has lots of pretty entertaining pictures, but I have a cool relationship in ellipses where c squared is equal to a squared minus b squared. And remember, a is half of the length of your major axis, b is half of the length of the minor axis. So then, if I write my generic equation, it's going to be x squared over a squared plus y squared over b squared is 1. So here's the very, very technical way that we determine whether I have a horizontal or vertical ellipse. So whichever variable has the largest denominator, and I'll show you a couple of examples, that's going to be a squared. And a squared, wherever I have the largest denominator, that determines the orientation. So I'm just going to give you a couple of examples. I don't know that I had actually written this down, but I'm going to go ahead and show you a couple of examples. I did not. So let's say I have x squared over 4 plus y squared over 9 is equal to 1. This is the bigger number. It's under the y, therefore, this is a vertical ellipse. Okay? And I would know A and B, and so then I could use this handy-dandy formula to find C if I needed to. I could find coordinates of my major axis, my minor axis. I could find coordinates of my foci. We can do all kinds of things once I know A, B, and C. On the other hand, let's say I have x squared over 25 plus y squared over 16 is equal to 1. The 25 is bigger. It's under the x, so therefore this would be a horizontal ellipse. So it's really not rocket science. It's actually fairly straightforward. Okay, and then I can determine the coordinates for my center, my foci, based on knowing all of this information. So just like with our other shapes, of course, we have to translate this. So I'm going to have x minus h, quantity squared, over a squared, y minus k, quantity squared, over b squared is 1. And remember that we're looking for the largest denominator. Whichever is the largest, that's going to tell you the orientation of your ellipse. Okay? The center of my ellipse is still going to be just like other things. It's going to be HK. Remember that the H always has to travel with the X because it is a horizontal shift, and then the K always needs to travel with the Y because it's a vertical shift. Alrighty, and I think that's all of the information that I need to give you for an ellipse. I'll probably think of something in a little bit. All right, we do have a new little formula to get that we did not use in pre-calc, and that is the area of an ellipse. Sorry, I can't spell. So the area of an ellipse, A, is equal to pi AB. And so actually, it's just kind of interesting because that's what tells me the area. The circumference of an ellipse is going to be pi A plus B. And there's all kinds of interesting math that gets us to these formulas. So this one is the circumference. But I think for us, this is going to be our primary information. I'm going to give you one additional piece of information, and we'll see it more when we do our polar coordinates. But we talk about eccentricity, and I'll go back and tell you that for the parabolas. Okay, so for my eccentricity, so this is a value E, and it's going to be C divided by A. Alrighty, that determines the eccentricity for all of our conics. And if C is less than 1 but greater than 0, if E is less than 1 and greater than 0, then that means that this is an ellipse. Okay, so while I'm writing eccentricity, let's do one for parabolas. If E is equal to 1, then I have a parabola. And if I have E is greater than 1, which you can't see, then I know that I have a hyperbola. And that's the shapes that we're going to talk about next. All right, so for our next shape, we want to talk about a hyperbola. And I actually think, I don't know that we're going to have to do that much graphing with these like we did in pre-calc, but the hyperbolas are the nicest ones to get a really pretty graph. So for a hyperbola, I have some asymptotes, and this will be y is equal to plus or minus b over ax. We'll talk about the conditions for that in a moment. So I have two asymptotes, and then I'm going to have a curve that's pushed by the asymptotes. This is going to be the vertex of my little hyperbola. Okay, this guy is the center of the hyperbola. Okay, the foci, just like other things, are always going to be inside the curve. So there would be a focus. There's a focus. The distance from the center to the vertex is A. So the distance from the center to the vertex is A. And then the distance from the center to the focus is C. Okay, so the distance from the center to the focus is C. And then in hyperbolas, they actually have a rectangle in the middle, which is kind of trippy. So it looks kind of like this. And so that distance would be B and B. But we actually don't use that very much when we're talking about a hyperbola. So this axis, I'm going to put him in black, is called the transverse axis. All kinds of vocabulary words. Okay, and the length of that is 2a. I have a handy-dandy little formula for hyperbolas that says c squared is equal to a squared plus b squared. I have two different formulas for the asymptotes. We'll talk about that. If it's a horizontal asymptote, then my equation is y is equal to plus or minus b over a x. And if I have a vertical asymptote, which means that its transverse axis is vertical, then I have y is equal to plus or minus a over bx. Now, a lot of different books at this point manage this information. When you guys were in pre-calc, we talked about the easiest way to graph a hyperbola is to find the center, graph your asymptotes from the center. So if I had a translated hyperbola, I could add those translations to this equation. But if you're really just looking for a pretty graph, it's easier to just go to the center, draw your asymptotes in relationship to the center of the hyperbola, find the vertices of your hyperbola and sketch. So it's really one of the nicest conics to graph and get a really nice picture. The standard equation is x squared over a squared minus y squared over b squared is 1. So the hyperbolas are the only conic that has both variables squared and a minus sign, because in the circle, the a and the b would be the same, and then I would have a plus. For an ellipse, one of these two guys is bigger, but I would have a plus. So for hyperbolas, the positive variable determines the orientation. It also determines A by default because A is always going to be under the positive variable. So just like in this one, or just like in all of our other shapes, I have to translate everything. So if I translate it, I'm going to have x minus h quantity squared over a squared, y minus k quantity squared over b squared is 1. So because, again, the x is positive, this would be a horizontal hyperbola. if I had y minus k, quantity squared over a squared minus x minus h, quantity squared over b squared is 1. If I had that situation, y is positive, so therefore this would be a vertical hyperbola. So this is the vertical hyperbola. And I think really all you need to remember is whichever variable is positive, and this is our horizontal hyperbola. Okay? So again, we talked about our eccentricity. For a hyperbola, the e value, which is c divided by a, is going to be greater than 1. Okay? And I have this handy-dandy formula to help me find c or b or whatever's missing. So those are called our basic equations, or our standard form of the equation for the circle, the parabola, the ellipse, and the hyperbola. Okay? So now what I want to talk about is this general equation. And again, it's information that we saw in pre-calc. We just haven't done it for a little while. Okay, so scoop my paper up. All right, so that one is going to look weird. It's going to look like ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. So that's the general equation of a conic, and it looks nasty. But the way that we're going to manage it is when I see an equation, I'm going to combine my like terms, I'm going to do completing the square, and then I'm going to determine what type of hyperbola it is. So for our example, let's do 16x squared plus 25y squared minus 64x plus 150y plus 279 is 0. Right off the bat, you can look at this and pretty safely determine what it is. The x and the y are both squared. There is a coefficient in front of the x and the y that is not the same, which means that it's not going to be a circle. It's in all likelihood going to be an ellipse, and I just need to finish the problem to determine which type of ellipse it is, whether it's a horizontal or a vertical ellipse. So my first step is to combine like terms. So I'm going to put my 16x squared minus the 64x, and then I'm going to do 25y squared plus 150y, and I'm going to move the 279 to the other side of the equation. Then I'm going to factor, so I'm going to take 16 out of this one, and I get x squared minus 4x, and I'm going to leave some space because I'm going to do completing the square. And then I'm going to factor the 25 out of this set, and I get y squared plus 6y, leave some space, is a negative 279. Now I'm going to do completing the square twice, remembering that I have to distribute this term on the outside. So half of 4 is 2, squared is plus 4, and then 16 times 4 is 64, so I have to add 64 to that side of the equation. And then half of 6 is 3, squared is 9, and 25 times 9 is 225. Okay, so now I've done the completing the square part. Now I need to just factor. So I'm going to have 16 times x minus 2, quantity squared, 25 times y plus 3, quantity squared, is equal to 10. Okay, remember a standard form, I want a 1 over here, so I'm going to divide by 10, divide by 10, divide by 10. And it's nice to do the math upside down, meaning that I want to do 10 divided by 16, so I can write that number down here. I could also leave it like this, and that's not the end of the world, but I'm just going to rewrite it to kind of illustrate a point. So I have x minus 2 quantity squared over 0.625 plus y plus 3 quantity squared over 0.40 is equal to 1. I know that the center is going to be at 2, negative 3. The denominator is bigger here, which means that this is a horizontal ellipse. And I know that's an ellipse because both variables are squared and there's a plus in the middle. Alrighty, and then I could actually find A if I wanted and B if I needed to, and then I could find the coordinates of other things. But that's kind of it. So that's just a crash course reminder of the work that we did with Conics in pre-calc. Alrighty, that's it for today. I will see you tomorrow.